This is the pre-lab talk for experiment number 6, redox titration. This is for Chem 120 lab. The goals for this experiment are to review and practice performing a titration and stoichiometric calculations that involve reactions in solution. We'll also practice thinking and understanding skill number 4, achieving high quality results. We'll accomplish this by making sure all glassware is read to the correct precision, namely our burettes during our titration. We'll improve our titration technique as we do multiple trials. And we'll also practice showing clear and complete calculations that preserve precision using our sig-fig rules. Finally, we'll take a look at a new technique, standardizing a solution of sodium thiosulfate. In our safety pause, we noticed that potassium ferricyanide is a toxic chemical and sulfuric acid is corrosive. All potassium ferricyanide and ferrocyanide solutions will be collected in a specialized waste container. And any solutions that contain strong acid will be neutralized before either disposing of in a waste container or flushing down a drain with plenty of water. Today's chemistry focuses on the chemistry of iodine. The oxidation of the iodide ion, I-, to elemental iodine in solution, I2 aqueous, and the reduction of the reduction of I2 to I-. We call this chemistry in this type of titration an iodometric calculation, or titration. Let's look at how this works. In part 1 of this experiment, we want to standardize a solution of sodium thiosulfate. We standardize solutions to determine their precise concentrations. Typically, this must be done for solutions in which we cannot know precisely the mass and therefore moles of solute that are present in the solution. This is true for sodium thiosulfate. Sodium thiosulfate is a hygroscopic material, meaning that it picks up moisture from the air around it. Therefore, when weighing the material, you're also weighing some unwanted water molecules that the solid is soaking up. Therefore, part of that mass is water, and you're not sure what part of that mass is water. Therefore, an approximate concentration solution is made. In this case, approximately 0.1 molar solution is made. And then we determine the exact concentration by performing a titration. In this experiment, we take advantage of the reaction between thiosulfate and iodine in solution to form S4O62- and 2I-. Now, in order for our standardization to work, we actually need a pretty well-known concentration of I2. This is not possible since I2 has an intermediate solubility in water, making it very difficult to determine its concentration. So we need to be able to, in a way, know the exact concentration of I2. So we couple this reaction with another redox reaction, the reaction between potassium ferricyanide and I- to form potassium ferrocyanide and I2 in solution. Now, it's pretty easy to weigh potassium ferricyanide. It's not hygroscopic and is easy to weigh out. So therefore, we want to relate the amount of potassium ferricyanide used to the amount of sodium thiosulfate that's in our solution. To do this, we make sure that our potassium ferricyanide will be, in essence, our limiting reactant. So we use an excess of I-. In doing this, now, in essence, our amount of I2 is known, since it depends on the amount of potassium ferricyanide that we added to our solution. Now we titrate our solution with sodium thiosulfate, which will react with the formed I2 until we reach our endpoint. To make things easier, we'll take the sum of these two reactions to get our final net reaction between the thiosulfate ion and the ferricyanide ion to form S2O6 2- and potassium ferrocyanide. This net reaction, which is a net ionic equation, can be used for all of our calculations of part 1, since it only shows the relationship between thiosulfate and ferricyanide. Notice that I2 does not appear in the reaction at all. So now let's move on to part 2. The chemistry is almost similar. We'll use a couple of redox reactions that involve I2 and I-. We'll use this first reaction as we did in part 1, the reaction between I2 and thiosulfate, but now we know the amount of thiosulfate. We're still not quite sure about the amount of I2. This time, we're going to look at finding the mass percent of copper 2+ in a copper glycinate sample. When copper glycinate is dissolved in water, you end up forming Cu2+ ions. These ions can react with I- to form copper 1 iodide, which is an insoluble solid, and I2 in solution. Our unknown now is basically the amount of copper 2+ that's in our solution coming from the copper glycinate. So now we've added, but once again, the amount of I2 depends on the amount of copper 2+ in solution. And therefore, we can, as we titrate the I2 with our sodium thiosulfate solution, we can therefore relate the amount of copper 2+ to the amount of sodium thiosulfate that's now in that we now know the concentration of. So therefore we can add these two equations together to relate the amount of thiosulfate and the amount of copper 2+, which is our unknown in this case. Notice that the net reactions are what you want to use when performing your calculations. Let's take a look at some procedural points. And I see that there's an artifact. This used to be experiment 2. So let's take a look at some of our procedural points. Sodium thiosulfate is pretty difficult to dissolve in water. To facilitate this, I ended up using a magnetic stir bar and a stir plate. We should also talk about the balance rules. And the main thing to remind you of is that we do not want to directly add any chemical to the analytical balance. Instead, we use our top loader balance to get a rough weighing, which is easy to add and remove chemicals, and then move the weigh boat to the analytical balance. In this case, we'll then weigh the weigh boat after adding our solid to our flask. We also want to make sure that we transfer our solid quantitatively. This is sort of why we want to weigh the weigh boat after adding to the flask. Even if there's a little bit of solid left on the weigh boat, we'll make sure that we account for that by taking the difference between the emptied weigh boat and the full weigh boat. We'll review here how we use our burette by noting that we must take our volumes out to the hundredth place. So therefore, even when subtracting your final and initial burette readings, you do want to make sure that you include that hundredth place, even if it's a 0. If you look at your procedure, there's actually a whole lot of different chemicals that are used to make our titration solutions. So let's go over them so that we're not confused. We'll also go over them again in the video. In our flask, we precisely weighed 0.5 to 0.7 grams of potassium ferricyanide solution, which we then dissolved in 35 milliliters of water in an Erlenmeyer flask. We then add 5 microspatula heaps of potassium iodide, which is about 1.5 grams, which is an excess amount of I- that we saw in our chemistry lesson. We'll then add 1 milliliter of sulfuric acid. Then let the solution sit for a little, and then add 12 milliliters of zinc sulfate. This is what we're actually going to be titrating. Note that when the zinc sulfate is added, a solid is formed in the flask. This solid comes from the solid that forms comes from the reaction between the zinc sulfate and the potassium ferrocyanide. This actually keeps the potassium ferrocyanide from participating in any side reactions during the titration, which might affect our results. Now for our burette. Our burette will contain our sodium thiosulfate solution. To make our solution, we'll weigh about 5 grams of sodium thiosulfate on the top loader balance. Note that it's not important that we know the precise mass of sodium thiosulfate, since we can't know it because it's hygroscopic. We'll dissolve it in about 200 milliliters of water in a 250 milliliter flask with the help of our stir plate, and store it until the end of lab. And we'll make sure that we fill our burette with that solution. Remember that when we rinse a burette, we want to rinse it once with water and maybe once or twice with the solution that we're titrating with, so that the burette walls are coated with sodium thiosulfate. We will do 3 trials of this titration. For part 2, our setup is slightly different. Now we'll weigh out between 0.25 and 0.35 grams of copper glycinate, which is dissolved in about 35 milliliters, and dissolve it in about 35 mils of water. We will then add some sulfuric acid, and then we'll wait a bit since we want to make sure that the solution is as clear as possible. And then we will add 5 microspatulas fulls of Ki, again to make sure that I- is in excess. This is what we're titrating. In our burette, we will put our now standardized sodium thiosulfate solution. Typically, we only do 2 trials for part 2, and a 3rd trial if necessary. The last thing we need to review is taking a look at how to deal with error in our calculations. As a review, we'll need to talk about standard deviation of the mean. Remember that the standard deviation is an average spread in our data. In the data on the right, you can see that the blue arrow represents the standard deviation. Most of the data fall within the spread that arrow represents, around the average, which is represented by the x. The standard deviation of the mean tells us our uncertainty in our average value. This is calculated by taking the standard deviation of the mean and dividing it by the square root of the number of trials. You can see that the red arrow is the standard deviation of the mean, which represents the uncertainty in the average value. When you report your average values with the standard deviation of the mean, remember to make sure that you report your standard deviation of the mean to one significant figure. This is because typically we know that one of our significant figures is an uncertain digit, the one that we make a guess of. You then round your average so that it has the same number of significant figures as your standard deviation of the mean. Therefore, as you can see on the right, the density that's reported is 0.986 plus or minus 0.009 grams per milliliter. This is standard for reporting an average. The only exception to the 1 sig fig rule we should note is that if the first significant figure ends up being a 1, then you have the option of also including a second digit. Another important thing that we introduced in this experiment is propagating error. When we do by the time we get to part 2 of our experiment and determine the mass percent of copper and copper glycinate, the error depends on 2 things. The titration we did in part 2, there's uncertainty in doing that titration. There's also uncertainty from part 1 of the experiment when determining the molarity of our sodium thiosulfate. There are many ways that we can deal with this error, but we're going to take a simple way by using the percent uncertainty. The percent uncertainty can be calculated for part 1 and for part 2 by taking the standard deviation of the mean and dividing it by the average and multiplying it by 100%. Note that your percent uncertainty will most likely have 1 significant figure or 2 if the first number happened to be a 1. So how will we use the percent uncertainty to propagate our error? Usually we would have to take a sum of the squares. There's different equations to do that, but we're going to make things simple, and you're going to, at the end, compare the percent uncertainty from part 1 to the percent uncertainty for the titration, your titration data in part 2. Whatever percent uncertainty is the largest will be your percent uncertainty for your mass percent of copper and copper glycinate. After choosing that percent uncertainty, you can use the equation in your report pages to calculate a more absolute uncertainty, or a standard deviation of the mean, for your mass percent of copper glycinate. Okay, that's everything for this experiment, guys. I hope you enjoy. I know it's a lot of calculations, but it's a really good analytical experiment.